So, how things going? Good? All right. I guess this is going to be a busy weekend for you guys. For me, it's a little less work in terms of preparation of the class. So, it's a good weekend for me. All right, so let's go over. Again, next Tuesday, it's going to be the big day. And basically, this is the summary. I guess so you guys had no problem to download this file. And I think if you can understand most of this contents in this slide and then discussion that we have today, it will be very easy for you to get more than 90% of the credit of the midterm. That's my expectation. But reality can be a little different, as always, right? So I will try hard this class to pitch in. And there's no multiple choice questions. Actually, I counted the problems. It's about 15 problems. And then there's, I think, 3 or 4 kind of calculation problem, right? Unit conversion, things like that.
You said there'd be one math problem.
So on the big problem, there's a couple of them. But it's not really math, right? It's, we will provide the equation, everything, and then you can plug in the number. That doesn't count? That's ours?
Let's review that.
Okay, we'll leave it that thing.
Are you using a specific type of calculator or?
Anything is fine. Just don't use your phone. So calculator will be fine.
I don't know if somebody already asked this or not. Scan or smog or?
What's that? No Scantron. You can just write in to the paper on the paper.
So you'll give us all the equations we need?
Yep. Nope. You don't need to remember any equations. So we'll provide equations, everything. And then there will be 10 points of extra credit questions here. And then I will be out of country from Saturday basically to next Wednesday. So if you have a question, come visit tomorrow. Visit me tomorrow, okay? I will just open my office from 9 a.m. to 5 p.m. tomorrow. So stop by. And this is a quiz question of that closed, I think yesterday, right? So I thought it's interesting. There's some wrong answers in the London type smog and the LA type smog. And then there's a number of wrong answers for the log. But this is not going to be on the exam, but let's just go over it, this thing. So again, the log scale is not about if it's 3 in log scale and 8 in log scale. It's not about 3 divided by 8. So some of you guys thought this is just like that. It is more like 10 to minus 3, 10 to minus 8. It's 10, 5, something like that. So it should be this one, right? So that was one. And then probably to prepare your exam, you should understand what's London type smog and then what's LA type smog thing is. We go over several times and then we will go over this thing again today, right? And then this is the homework. I guess you guys got your homework back. So this is a distribution of the score. And then the full score is 80. So a lot of you guys got the 80. That's good news. And then most of you guys got the more than 70, which is pretty good score, right? And then I didn't put that slide of their point distribution, but I think this midterm is like 20%, something like that. Is that right? 20 or 25% only, right? So 25%. So the theory is if you can get the full points for quiz, attendance, and then homework, which is relatively easy to get. If you visit your TA or me, we just provide all the answers, basically. And then if you just get the full points for the homework and quiz, and then attendance. And then if you just get the half of the midterm and final, it will be very easy B for you guys. Okay, that's kind of strategy. If you care about the grade. So this is a second homework set. I guess I emailed you guys this homework set, and then I also uploaded this thing on the class website. Is that first one? This is first one, right? Sorry about that. So everybody got the second homework set through email? Okay. So that's due November 1st, I think. Yep. 4th? Okay. 5th? Okay. Okay. 5th. So whatever that I wrote on the homework set, that's the due date. So we will be very generous about providing answers if you visit us, if you don't have no idea what's going on in terms of the homework and then quiz. But we will really precisely keep the deadline policy. So there will be penalty if you don't submit earlier than deadline. So that's something that I'm gonna precisely keep. And then there's something that I expect. So please submit your homework on time. Then there will be a penalty on it. So what I should go over? There will be something very similar with this question will be on there.
Third one?
Yeah.
Great.
So that's the only calculation related, math related question that I put on the exam. So we will go over it.
Is there, like, what is that called? So if we wanted to look it up online for, like, more studying, do you know what I mean? Like, is,
I will go over it right now.
okay.
We have around an hour and a half from now, so hang on there. So I think so. We will go over most of this thing today. So let's go over it. So first thing is that air pollutants are stuff, but stuff is not really scientific term. So I expect you guys understand what air pollutants or generally stuff or material is composed of, right? It's the basic unit is atom, and then atom is neutral. Then it consists by the proton and neutron and electron. And if there's imbalance between proton and electron, that becomes ion, right? So atomic mass is determined by the proton and neutron. Actually, you don't really need to know about this thing, but only you need to know is the atom and ion. And then element is that something, the single atom or the material that composed by the single atom. The molecule has the electric the bonding between the atom, and then, for example, molecular oxygen, molecular nitrogen, ozone, things like that, composed by the multiple atom. We call it molecule. And then the characteristic of the molecule is that it has bonding inside, right? So that's the one thing. And then isotope is same atom, but different number of neutrons, has different mass in it. So it has same chemical characteristic, but different masses. So this is, what we call air pollution class. So I want you to remember this whole thing, okay? So there are three important aspects in this definition. It should be anthropogenic, which is human-made, right? So naturally occurred thing in the atmosphere is not air pollutants, right? It should be human-made, more fancy word, anthropogenic. And then it can be both gas and particle, right? It can be particle and gas. We already discussed about particle and gas because both gas and particle can become air pollutants. And then those gas and particle accumulated in the atmosphere are high enough that can damage their human health and then plants, all sort of things. And then we call it air pollution, okay? And then those gases and particles, we call it air pollutants, okay? Clear, right? So, so some of these things will be on, obviously, in the exam. And then, for example, we will provide, if I ask you to convert Fahrenheit to Celsius, Celsius to Kelvin, things like that, then we will provide all this equation, and then all these scalars in the exam, okay? And then we usually have notate the mixed concentration of air pollutants, especially gas species, as mixing ratio. ppb is 1 molecule out of billion molecules, right? So ppt is 10 to 12, and then ppm is 10 to 6. So we will discuss about it a little further as time going by. And this is one question that I put on the exam first, not exam, homework, right? So sun temperature is 6,000 Kelvin. So it will follow that green line right here. So that's why mostly it is emitting the visible wavelengths. And then I asked if sun is half of temperature of the current sun right now, then it's going to be more like looking like this, right? So it's going to be much darker. That's simple answer. That Earth's surface is going to be much darker. But there's a lot of creative answers that we read. And then Ian entertained all those answers. So I think most of you got the full points for that aspect, if that is reasonable. Okay? So that's the simple answer for that homework question. Okay, this is a more close view about electromagnetic radiation that we are interested in this whole class. Visible wavelengths, obviously we are interested in it because this is basically the energy source from the sun to the earth. And then what's the wavelengths shorter than visible wavelengths region is UV, right? So UV is very harmful to us. So basically ozone layer up in the stratosphere protects us from the UV. And then the wavelengths that higher than visible wavelengths region is IR, what you call it, infrared. And then we sense this electromagnetic radiation as a heat, temperature. So, so Earth's electromagnetic radiation is mostly this IR region. So the global warming is mostly related with this electromagnetic radiation region called IR. So, so we will discuss about this ozone layer chemistry in the stratosphere second half of the this quarter, and then also we'll discuss about global warming during the second half of this quarter. So I just review this whole material first half of the quarter because obviously you need to take the exam, but also there's something you really need to remember to understand second half of the quarter. Also, there's two reasons behind that. So I guess that's all you need to know for the exam. And then this is another kind of explanation of the solar electromagnetic radiation. So again, when you see the this plot, then you gotta take a look at the x-axis and then y-axis. Y-axis is obviously energy, and then x-axis is wavelengths, and then the peak wavelengths that sun emits is visible wavelengths. And then if you go to higher wavelengths region, that means lower energy, which is IR, sensible heat, then UV, which is very harmful for the human, and then plants, also animal, things like that. And then okay, one other thing, we will discuss about this pH, so log scale a little further, second half of the class. So this, if you take a look at the axis here, from here to here, this is 100 times, 100 times, 100 times, and 100 times there. So this is log axis scale. So it is not linear axis scale. So that's the very convenient way to plot the large range of the number in the one graph. So we'll discuss about this a little further down there. So, so from this table, all you need to remember is Earth is 4.6 billion years old. And then it is very recent history that Earth's atmosphere just looks like now It's about the 500 million years ago that oxygen composed about 20%, nitrogen composed about 80%. Then before then, Earth's atmosphere looks very different, and then actually the interaction between atmosphere and plants mostly change the composition of the atmospheric gas constituents. So that's the main thing you need to remember from this plot. And then we talked about what's the really essential gases that maintain life in the atmosphere. We talked about water, right? And then of course oxygen, and then photosynthesis. For photosynthesis, plants need CO2. And then we talked about ozone also, because ozone in the in high atmosphere, somewhere in between 20 to 40 kilometer, this ozone layer actually absorbs this UV, which is radiation below 250 nanometer, absorbed by the ozone layer right here, and then not much of UV actually gets into the surface. That's how the human and then plants and animal can live on the surface out of the water. So before this ozone layer, we believe that most of the living form actually living in the ocean to avoid this UV energy. Okay, so that's all you need to know from this slide. And then chapter 2. Let's go to the chapter 3. The main thing was the chapter 3 was pressure, volume, and temperature, and then how they are related, right? So the pressure distribution over the altitude, you may think that pressure is constant or decreasing linearly over the altitude. No, that's not the case. Pressure is exponentially decreasing as a function of altitude, right? So basically this photo illustrates that how air molecule is distributed over the altitude. So it is highly dense on the surface. If you're just going up high, the number of molecule is decreased. So I just related with pressure and then number of molecules kind of the same time, because number of molecule in given volume determines the pressure, right? So that's the basic idea of the pressure, volume, and temperature. So again, most of air is composed by the nitrogen and oxygen. If you add this thing up together, it's almost 99%. And then if you just take a look at just 1%, most of that 1%, other than nitrogen and oxygen, this inert gas, argon, neon, helium, and krypton and xenon, which is not air pollutants. So air pollutants are really, really tiny fraction of the air constituents. So that's the main points that you need to remember here. So it's good to remember that nitrogen is about 78%, and then oxygen is about 21%. It's kind of common sense, I guess. So we talked about this magic equation. I don't expect you need to use this magic equation directly for the midterm, but you need to at least need to have some conceptual understanding in this equation. Basically, you can rearrange this thing one to the other. For example, pressure. So this is constant, right? And then this is basically number of molecules. And then this is volume and temperature, right? So in this, if constant volume, if you set the volume constant, if you increase the temperature, then pressure is going to be increased. If you decrease this thing, it's going to be decreased. So this is all you need to know, for this class, that how those different seemingly independent parameters are related to each other. Okay? So again, this is that thing. And then we discussed a little bit about CO2, but we will discuss a lot about CO2 while we discuss about the global warming or climate change, if you don't like that term. Basically, CO2 has been increased because we just bring in this carbon down the Earth, and then we just emit this carbon as form of CO2 to the atmosphere, so which is notated right here, right? And then there's another very important factor you need to know. is photosynthesis, right? Photosynthesis basically using CO2 and then make that organic material, which is plants. What's the organic compounds we talked about? Carbon-based, right? Where's carbon in the atmosphere is CO2, okay? That's how organic compounds made up in the natural system. Basically, this tree absorbing CO2 and then making some, using the carbon in the CO2 and then making some organic compounds in the atmosphere, right? So, so we discussed about this plot, I think twice. So let's do it 3 times this time, okay? So CO2 has been increased over time. Why is that? Because of this fossil fuel use by human, right? And then what's this thing here? Is the annual cycle thing. It's this thing right here, plants, right? So now everybody understands this thing. So if you take a look at this plot, that you can understand, you can get the 2 information out of this: the increase of the CO2 concentration over 50 years, and then this annual cycle, which is one by the human, and then the other by the natural system, which is plants, right? Should I do this or not? So this is some discussion that we will do, because we have time. Just why not? Just let's do it. We will discuss about actually second half of this class about how CO2 is kind of behaving in the atmosphere. Then most of them is absorbed by the plants. There are a lot of them also observed by the ocean too. And then that actually, this magic, to understand this magic, you need to understand a little bit of chemistry, which you guys are not that big fan of, I guess. So basically, this CO2 gas in the atmosphere dissolved in the water, and then it becomes this carbonic acid. And then we talked about pH during the when Ian discussed about the particle. So basically, acid is any molecule that can provide hydrogen ion to the water, right? So basically, if you have too much of a CO2, so the bottom line is that then you can actually acidify seawater. So have you guys heard about ocean acidification, things like that? No, not really. So this is how actually man-made CO2, human-made CO2 can acidify seawater, and then we will discuss about this whole chemistry and the implication of this thing second half of this quarter. So this is brief introduction, but this is not gonna show up your midterm. But just introduction, because it's obviously there's a lot of students are here. You guys are widely wake up, so I just want some introduction. Yeah? So we talked about EPA designated 6 air pollutants. And then I want you to remember this whole thing also for the midterm. So we talked about this guy, and then this guy is the first example that kind of a conflicts between new technology and then environmental implications, and then how public in general, society is dealing with any side effects of the new technology, things like that. And then we watched kind of a lengthy video about this guy. So just briefly review what this guy did, and then what this guy's invention was, and then what was the side effects of the inventions. So that's good to remember, I guess. And then we discussed about London smog, and then LA type smog, right? So coal. So this is also related with the one of the quiz question that I asked about what caused London type smog. So this is a really complicated molecule. Probably nobody can, even very famous chemists probably cannot write this molecular composition of the coal. But what you need to see from this molecular structure is that what kind of atom are composed this molecule. So we talked about this stick thing, is there's carbon, 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 and then there's too many carbons there, so we don't bother to write carbon, and then we just make a stick. So if there's a 6 carbon compounds like this, then we just draw like this, right? That's how we draw the organic compounds. So if we take a look at this core molecule composition, then there's a lot of carbons in there, right? There's a lot of sticks. And there's some, you can see some sulfur here and there, and then some hydrogen and oxygen there. So basically you can expect carbon combustion will make CO2, which is complete combustion we call it, and then CO, which is incomplete combustion, and then sulfur will make SO2, right? And then obviously coal burning makes a lot of soot, which is particle. Right? So that's all you need to know. And then in the London type smog, there's no secondary products in terms of photochemical reactions. So these pollutants are accumulated in the surface with the help of the meteorological setup, usually winter time, when atmosphere has temperature inversion, which means that atmosphere gets very stable. There's not much particle mixing going on. So a lot of these pollutants get accumulated in the surface, and that cause smog. So that is usually happening during the winter time. So we watched several videos. It was all happen during the winter time. Okay? So that's the two things. Emission of the air pollutants from the coal, and then these guys right here, mostly from burning, and then meteorological setup require that very stable atmosphere in the surface area, which happens usually during the winter time. So, okay. So then LA type smog is totally different thing. That's LA type smog is mostly from pollutants from car exhaust, which is, this is chemical composition of the gasoline. So it's all about carbon. So there will be CO coming out. And then these compounds are highly volatile. So this organic compound can evaporate to the atmosphere too, right? So we call it VOC, volatile organic compounds. And then most important thing is NO and NO2. We call it NOx, right? So these are LA and London. So these are totally different things, okay? And then the steam engine that use the coal, right? And then we talked about the reaction a little bit before we discussed about this LA smog, because this LA smog eventually, this thing makes the ozone. That's from the chemical reaction. So we discussed about a little bit about reaction here. So basically, one molecule, the other molecule hit each other. There's two possibilities. One is that they are just bounce back each other or make some reaction, right? So there's two factors that determining reaction rate. One is concentration of these reactants, right? And then a possibility of reaction, which is expressed by reaction constants, right? So we talked about this thing. So we mostly discuss, to understand this LA smog, we need to understand this bimolecular reaction. It sounds fancy, but basically it is saying that just two molecules hit each other and then make reaction, right? That's what we call bimolecular reaction. That's a fancy way to call it. And then photolysis, which is the molecule hit by the photons from the sun, and then it dissociated. So that's by definition photolysis, okay? So that's it, that's it. So let's take a look at this photolysis a little further. So this is the most simple way to understand the, this reaction dynamics. So NO2, photon, NO plus O. So let's take a look at this NO2 decrease rate. So if you have NO2 in the atmosphere, then there's sun there. Basically what this reaction dictates is that so some of NO2 is going to get the photons, and they will be dissociated to NO, right? So that's what this reaction is. So let's assume there's time and then NO2 concentration, right? So the sun is here. Let's assume there's 1 ppm or ppb or ppt of NO2 in the atmosphere. Then as time going by, then it's going to be decreased like this, right? Because of the photolysis. And then how fast it's going to be decreased, it's going to be dictated by the reaction constant, which is J, right? So we can call it decrease of NO2, or mathematical expression. So in the given time, NO2 concentration change, right? In this case, it's going to be minus because it's going to be decreasing, right? So this is exactly graphical expression of this thing right here, right? So that basically this decreasing rate is going to depend on NO2 concentration. If there's more NO2 molecules in the atmosphere, then more NO2 molecule is going to go away. And then what's the other factor here? Sun. Solar radiation, right? If there's more solar radiation, then it's going to be more, this decreasing rate is going to be more faster than the least solar radiation, right? Is that clear? I can see a lot of confused face. Really? Okay. So so there's 100 NO2 molecule in the atmosphere, and then 10 out there. And then solar radiation is about the same, okay? Then if we assume that there's 10 molecules go away in 1 second, then how many molecules is going to go away if it is 10? What's that?
The other 10, right?
You think it's 1?
Why?
Why? That's a very interesting question. That's very difficult to answer. Okay. Basically, photon hits NO2, right?
Okay.
And then available photon is about the same in this case and that case, right?
Right.
So in terms of the frequency that photon is going to hit each NO2 molecule, it's going to be 10% basically. Isn't it?
Every single time?
Yeah. No. So basically, available photon dictates that about 10% of NO2 molecule is going to be dissociated. So if it is 100 molecule in the atmosphere, it's going to be 10. It's going to go away, and 10, and then it's 10%, which is 1. Clear?
Yes.
Really?
That's
Okay. We'll find out when I grade your midterm. So where were we? So yeah. So basically, the NO2 concentration is one factor, right? Then the other one is the solar radiation. Basically, this thing, so basically what fraction of the NO2 is going to be dissociated? That's dictated by the solar radiation, right? So here we call it J, which is photolysis rate. This is how we express And then I will give you some quiz here. So let's say this is JNO2 is 1, right? What it is gonna be this 0.1. It's gonna be this or that. A and B if JNO2 is 0.1. So this is 1, your reference point. Then if JNO2 is 0.1, it's going to be either A or B. It's not a trick question. It's very straightforward. Remember this. Want to do the little clicker thing or? No, you want to do a clicker thing. Shoot it. It's A or B. Yeah. So basically JNO2, so it is 10 times less possibility NO2 is going to go away in terms of rate, right? So if it is 1 and then you have 100 molecule right here, then in the given time, 100 molecule is going to go away, right? So if you put the 0.1, 100, so what is going to be 10, right? It's going to go away. So no, actually it's A. I guess it. Confusing?
Yeah.
It's A, right?
Yeah.
How many people get it? Tiny. Let's do it again. Sorry. So you can remember this equation of actually what if I provide this equation, right? Right? Let's do it again. So basically if you have a sun and then NO2 molecule in the atmosphere, because the photon from the sun is going to be dissociated by this reaction. You understand this part, right? It's kind of clear, right? So, and then basically this decreasing rate is depend on NO2 concentration in the atmosphere. I guess this is clear. And then JNO2 basically dictates how fast NO2 is going to be decreasing, right? Let's assume this is 1, JNO2. And then for JNO2 is 0.1, which means that the decreasing of NO2 is slower, right? Just see this equation. This is decrease of NO2. And then if you decrease this thing, that NO2 decrease is going to be decrease, right? Yes. So what's the NO2 decreasing, by the way? So that's initial concentration of NO2, right? So decrease of NO2 is this much, right? Is that right? Right? So if you put the plug in 0.1, your decreasing rate is less, right? So it's going to be like that. Clear? Yes. How many people are clear? A little more. So it's going to be a little more clear if we take a look at the NO. Okay? So basically, NO2 decrease is directly related with NO increase, right? Is that right? So amount of decrease of NO2 is going to be increase of NO, right? So this is NO2. I have a green here. NO. So what it is going to be? It's going to be exact opposite like this, right? This is going to be NO. And then the formation of NO is going to be less like this. NO. Is that too much? Okay, then let me try once more. Okay? So let's assume three scenarios. Also, it's not flat, but this is hypothetical way. So sun is up there, sun is here, sun is here. So J value, photolysis rate is going to be highest at noon time, right? So it will be a little less because it is basically photon, number of photons gets into the atmosphere. It's going to be that's the least in this case, right? During the sunset or the sunrise. So J, NO2, let's say A, B, and C. And then A, B, and C. It's going to be just like that, right? Just stop me if you can understand this thing. NO2 concentration is right here. Let's assume in case of B, NO2 is going to be decreased like this. So you understand that NO2 is going to be go away, right? You get that far, right? Everybody get that far because of this reaction. And then NO concentration is going to increase like that, right? Because when this thing go away, NO is going to be produced, right? So that's B, right? B. So let's think about A. So basically, JNO2 is high. And then if you take a look at that, decrease of NO2 is directly positively related to JNO2, and then concentration of NO2. And then this is set, right? So what if we have high JNO2 value, higher JNO2 value? Then NO2 is going to be decreasing much faster, right? Which one is going more faster, A or B? B. I can see more B here. So that's scenario A, right? So NO is going to be produced more, right? So where's the C? Going to be above of the A, right? Yeah, I use dotted line. Longer dotted line. So C, the production of NO is going to be less, right? So how many of you guys get this thing? Yeah, I guess. If you don't, come see me tomorrow, okay? Please.
So what would like a test question or like a midterm question be for that?
Almost exactly like this. Yeah. But I will ask something different, but if you understand this thing, then you'll be fine. What do you think, Ian? He already read the midterm. It's very close, right?
Yeah.
Yeah.
That's fine.
Yeah.
Yeah, as long as they understand like what the magnitude of the J value,
Yeah.
stuff like that.
That's one thing. So for the let's see, for the homework question, I asked about conversion between mixing ratio and number density, right? So basically, let's assume one ppb, which is one molecule, out of 10 to 9 molecule. And then you don't need to remember this calculation. So I will provide number of molecule in the given volume. Usually 1 atm is about 2.5 times 10 to 19 molecule. So let's say this is compound A. So how many molecules actually in 1 cubic centimeter if there's a total number of L molecule? It's just like that. Right? That's what it went through, right? If you are not really familiar dealing with this big number, you can do it separate way, right? You can just calculate this thing 2.5 and then this thing basically 10, 19 minus 9. So this is going to be 2.5 times 10 to 10, right? So don't try to put this whole thing in your calculator, you know. You can just put this thing separate and then that thing separate, right? Did I add a little more confusion here? Sorry, just use your calculator whatever you want to. I thought this is much easier, but obviously that's not the case. So this is clear, right? If I give you the number of molecule in the given volume and then give you the mixing ratio, you can calculate the number of molecule in the given volume for specific molecules.
Yeah.
Yep, go for it.
Can we do one more example?
Okay. So let's say 60 ppb of ozone. Let's assume so what is this total number of molecules made of? Mostly, we talked about it, nitrogen and oxygen, right?
Yes.
So we want to know real number of molecule of the ozone in this 1 cubic centimeter of the volume. So what do you do? What's the number that I should plug in?
6 times 10 to the 9.
6?
60 over
60, right?
Oh, right, sorry.
Yeah. Right? So what I would do is that minus say this is 10, 5, no, 15. So right? But from here you can use your calculator, right? Yep.
And you got 60 from.
Oh, this is 6, 9. But
Oh.
I just moved this guy right here. Sorry for the confusion. So from here, your calculator will take care of it, right? So all you need to do is that come up with this thing, right? But that's something you can do, right? Easily. Okay. This is again that dynamics of that. You don't need to remember the lifetime. Can I move along? Okay. So we talked about this ozone production in the troposphere, right? So we discussed, and NOx is important, right? It's doing cycle. So what is this thing? It's photolysis, right? And then produce this extra oxygen atom here. Then that react with the molecular oxygen, produce ozone. right? All right. Let's see. So from here, this reaction right here, ozone react with NO. So ozone react with NO, right? And then produce oxygen, right?
What is this? I don't understand what this is showing exactly. Just like
So let's take a look. Yeah, reaction, right? So when
one ozone or two?
so this side is forming ozone, right? From here, NO2 and oxygen. Then NO2 produce molecular atomic oxygen and produce that reacts with molecular oxygen and produce ozone, and NO, it becomes NO, right? In this side,
Okay.
right? Right? And then if you take a look at this side, then NO reacts with ozone, that becomes NO2, and then it becomes molecular oxygen. Basically, this reaction right here. Where is it? This guy. This guy, right? Actually, there's oxygen is missing here. So that's the last reaction should be ozone, right? So that's this side.
Okay.
And then this side is basically these two. So that's how this NO2 cycle produces ozone in the atmosphere.
Okay.
So do you think if I just remove these arrows, you can fill in the arrows?
Yeah.
Just like that? You think you can do that? Okay, then you are good. You guys definitely can do that?
Yes.
Really? That's great. That's great. Okay. Okay. Then you are good. I will find out actually. Actually, last year, I got the same responses. Yeah, we can do it. And then I got about half of the right answers actually. What's that?
Can you go back to it?
Oh, sure.
So we can look at it.
Would
Okay.
it be this one or this?
So,
This one, the simple one. Let's go for simple one.
so it matters like which side it has O2 pointing to O3, and so and O3 pointing to O2.
No. So basically, let's take a look at. So the punchline is that when you make to NO to NO2, what's going to be happening? You lose ozone, right?
Yeah.
So if you draw this thing, that dictates this line, right?
Yeah.
If you draw like this, then it should be like that, right? Are you sure?
I don't understand what it's showing.
Okay.
I just,
You don't understand
it's
what.
just like circles and arrows to me.
I think he just said it's how.
So I'm not saying that you can just draw your arrow just whatever you want to, right? It should make sense, okay?
Yeah, it doesn't make sense to me.
What's that?
It doesn't make sense to me.
So all of
Oh, you guys think that you can just draw whatever you want to, right? No, okay.
I'm wondering like what this is showing. Is this the like the reaction needed to convert NO and NO2 into oxygen?
Yeah. So basically, if NO becomes NO2, that basically destroys ozone to molecular oxygen, right? So let's go this side, right? NO to NO, that will make molecular oxygen to ozone, right? So are you still confident about the drawing arrows right way? Really? Okay, let's find out. What's that?
I'm not good with the math.
Oh, I see. Yeah, that's not really. Okay. No. That's not really. Okay, let's go for it. No, that was not my intention. That's not what you're thinking. Where were we? Yeah, so here, that's production of ozone, right?
Yes.
And then this is destroy of ozone. And then to produce more ozone, what do you need? You need to substitute this cycle right here other than ozone, right? That's what you need to produce more ozone. And then what other compounds that can do is CO methane, and then what the other thing? The last one. Whole foods thing. Organic compound, that's right. Volatile organic compound. Actually do this cycle instead of destroying ozone, then making this cycle. Okay?
When you post it online,
Yeah.
can you add the plus O2 on the last slide? Because on
This
the
one?
O3 plus.
I think it's already on there on the website though. But I can put the revised one.
Yeah, 'cause
But,
I think it's important.
That's very important actually. That's very important. Okay, I will do it. I will do it immediately.
Should we memorize those equations?
You think that will help to draw the arrows right away? Then you don't need to.
Counterclockwise, clockwise.
You know the thing is it should make sense, right? So let me so I think I come up with a very easy way you can draw the arrows. So if I just miss this whole arrow thing, what you gotta do is what you gotta do, make an arrow from NO to NO2 and then NO2 to NO, right? So without this thing, so you don't want to make an arrow in the both NO is going to this and this, right? Make a circle, right? Then you have oxygen in here. So let's take a look at this. What this is gonna do? This is gonna do is that basically NO need one more oxygen atom, right? Where it can be coming from? Ozone. So ozone should go to that way, right? I really want to make sure that you guys, every one of you guys understand this thing. This is so important. This oxygen, so if NO2 go to NO, basically that lost that one oxygen atom, right? So what that's gonna do? Molecular oxygen becomes ozone, O3, right? I will be very disappointed if one of you guys miss this problem. Okay, this is ozone and VOC, reactive organic gases, things like that. So you don't really need to this thing. And then we talked about Los Angeles is a big place in terms of the ozone production because we have sunny weather all the time. Why sun is important? Because this photolysis reaction, right? This light is important for ozone production. And then there's a lot of cars in Los Angeles Basin, which makes a lot of NOx, and then VOCs in the atmosphere, which is basically cycling this cycle, and then the VOC is actually make this cycle without destroying ozone, right? So we discussed about this thing in perspective of Los Angeles. And then actually you need to understand this thing not for exam, but for next homework question. So let's skip this thing. And then we talked about biofuel. Also, this is also related with the next homework question. So to decrease the confusion, let's skip this thing. Particle, that's what Ian went over. So that's 3 modes of particle we talked about, which is small, medium, large. That's a good way to put it if it is your jacket, things like that. But we usually call it, scientists usually just make up totally different non-real world to discuss about the natural phenomenon. So we developed the words called nucleation, accumulation, and coarse mode. And then this size is much smaller than what you may think of as in terms of particle. For the nucleation mode, it's less than 100 nanometer. And then accumulation mode, about 2.5 micrometer, which is what they call it PM2.5. PM2.5 means that particulate matter smaller than 2.5 micrometer. And then coarse mode is that basically particle size bigger than 2.5 micrometer, right? So this is the how mode works, that most of the particle is kind of centered in about the 100 nanometer, and then 2.5 micrometer, about 10 micrometer also has 3 different modes. That's what we actually usually observe in the atmosphere. And then we'll discuss about it later, and then source, things like that. It's all about memorization, so you can just go over this thing. And then this one. So basically surface wind. So last lecture we talked about this thing, right? So so wind is coming out from the high pressure system in the surface, and then coming into the low pressure system. And then in the high pressure system, because wind is basically air molecule is going out from the high pressure center, the air is suppressing the surface. So usually in high wind pressure system associated with very calm weather, so high pressure system usually worsening the air pollution problem. Then low pressure system, this upwelling of the air motion that usually associated with condensation of water vapor in the atmosphere that makes cloud and the wind, all sort of thing, rain. So usually during the low pressure passage, air pollution problem usually getting lighter. Okay, that's the relationship between high pressure, low pressure system, weather system, and then air pollution. Okay, so that surface, and then above the air, because of there's no friction in the low pressure system, moving following this pressure gradient line in the northern hemisphere, because due to Coriolis force, it is rotating in low pressure system in the counterclockwise. Basically, the air is moving into the low pressure system side, and then due to Coriolis force, it just makes right turn, right? In the high pressure system, the other way around, air is going out and then make right turn, like this. Okay? So this time scale, yeah, this is kind of bottom line and then punch line. I really want you to remember this time scale, time scale thing. Basically, northern hemisphere and southern hemisphere, it takes about a year to actually air get circulated, totally mixed up in terms of air masses in the troposphere. And then it's much efficient to the west, from west to east, because Earth is rotating. It's kind of combination of Earth's rotation and the Coriolis force together. And then it takes much efficient to air pollutant transport from west to east side. And then even inter-hemispheric mixing takes about a few months, right? So that's what this figure indicates. So that's about it, I guess. So if you remember this far, I can guarantee you can get, I think, more than 90 points very easily.